Hello everyone. This is about a problem which I came across while working subsea on a subsea job. Let's consider this is my vessel which is submerged to a height h in water. Okay, and I have this flange at the bottom which opens a hollow cylinder up to the top, and it is bolted, and I need to open this flange. Okay, now let's have a detailed look of this. I've magnified this view, and this is how it exactly looks. This is the hollow cylinder which has an internal diameter d2 and an outer diameter d1. Now the flange at the bottom of the cylinder which has closed it is the bottom end of the cylinder has a diameter d1, which is the outer diameter of the cylinder, and the cylinder is hollow. It is just filled with air from inside. Okay, now when my diver went down and he unfastened all the bolts, we expected the flange to fall off on its own, but that did not happen. Now let's analyze why it did not happen and what can be done to make it fall off. So let's consider the height of the immersion of the cylinder or the ship as h, and let's consider the hydrostatic pressure. If rho be the density of the fluid, g be the acceleration due to gravity, and h be the height of the water column to which the cylinder is immersed in water, what happens is F upward, the force upward, is equal to pressure, the hydrostatic pressure, times the area of the flange. The area of the flange is pi d1 squared upon 4, assuming it is a circular flange, and obviously it is. So P is the upward force is equal to P times pi d1 squared upon 4. This is my upward force which is acting on the flange. As you can see, I have put in this arrow, and I have the weight of the flange acting downwards, but in this case the weight of the flange, the upward force, is much more greater than the weight of the flange itself, and that is why the diver is not able to pull off this flange even after unfastening all the bolts. Now let's see what we can do to assist the diver in removing this. First of all, what we did is we put in some weights from this cylinder. This is accessible. We put down some weights from here so as to increase the downward force on this flange, but it did not help. Now the easier method is, and we will implement this. See, the downward force is Fd equals pi d2 squared upon 4. If I fill this with the same seawater in here, I mean the same fluid of the same density which is outside, then the forces should cancel off. But here lies the twist. Why the forces will not cancel off at the same height is because, see, I have the downward force. When I fill this, the weight of water will act downward and push this flange downwards, but both having the same height will not be able to separate the flange. Why? Because, see, my downward force is given by P times pi d2 squared upon 4, and again P, hydrostatic pressure due to this column, is given by rho g times x. I'm sorry about this mistake. Rho g times x. Okay, the downward force. Now here again it is getting reflected, rho g times x. Okay, rho g times x into pi d2 squared upon 4. This will be the downward force. Now see very carefully, let's analyze the problem very carefully. d1 is greater than d2. As you can see, the pressure due to this water column will act on an area, will act on a circle of diameter d2, and the pressure due to this water column, the outer water column, will act on a circle of area d1. Now let's come here again. d1 is greater than d2. Now if we have the same height, the upward force will obviously be greater than the downward force, because your d1 is greater than d2. Now for both of them to get equal, let's equate both. Fd is equal to Fu. Now this is my F downward, rho gx times pi d2 squared upon 4 is equal to rho gh times pi d1 squared upon 4. Now this is the height up to which I need to fill the water inside the hollow cylinder, so that both the forces become equal. I cancel out the commons on both the sides, and this is how I arrive at the height to which the water must be filled in the hollow cylinder so as to have an equal force, and anything higher than this will exert a force which is greater than the upward thrust and push the flange out. Now x is equal to h times d1 upon d2 the whole squared. Now let's have a dimensional tally of the final equation. X is distance, h is also a distance, and d1 upon d2 is a ratio, which means it doesn't have a unit. So we are having a dimensional tally of the equation, so the equation is dimensionally correct. Okay, so in order to cancel out the thrust, the upward thrust on this vessel, we will have to fill this fill water inside the cylinder x, which is given by h times d1 upon d2 the whole squared. So the problem at the initial stage did not appear tricky, because we expected that once the diver unfastens all the fasteners, the flange will fall off by itself. But when the flange did not fall off, it put me into the thinking mode, and this is how I have analyzed it. Please tell me in the comments. Thank you.